Hi everyone, I am Lu. I'm from Data Management and Biometrics Group of University of Twente, and today I'm going to present our work, Resolution Invariant Medical Image Segmentation using Fourier Neural Operators. There are going to be 4 sections in this presentation. First, I'm going to give you a short introduction of this paper, and then the details of our approach, then the experiments and results. Finally, we have the final conclusion. So let's start with the introduction. What is resolution invariance in image processing? Basically, it means maintaining consistent performance regardless of changes in image resolution or size. So in specific context of medical image segmentation, resolution invariance serves the purpose of generating high-resolution segmentation using models trained on low-resolution images. So this property is particularly valuable for tasks such as medical image analysis, where precise delineation of structures is critical for accurate medical image analysis and diagnosis. In medical image segmentation, supervised learning models such as UNet, based on the convolutional neural network, rely heavily on labeled images, demanding expertise for accurate annotations. So, obtaining of higher quality labeled medical images is challenging due to the time-consuming and labor-intensive work of annotation process. So with resolution invariance, enhance the clinical utility of image segmentation models. It contributes to improve accuracy and reliability in diverse medical scenarios. So in the current medical image segmentation research, there's a lack of studies focusing on achieving resolution invariant segmentation. Typically, we use resolution invariant or super resolution techniques for image reconstruction and addressing image degradation, but it's not common to use it for image segmentation. Using resolution invariant techniques can increase the quality of segmentation models even when trained on limited labeled data. So in this presentation, we proposed the integration of Fourier neural operator into neural network architecture for resolution invariant medical image segmentation. Originally, Fourier neural operator is designed for solving partial differential equations. So unlike CNNs, the Fourier neural operator does better in learning maps between potentially infinite-dimensional vector space. As shown in Figure 1, our network consists of 7 layers, assuming the original images are one-channel grayscale images. So before we plugging them into the network, we apply positional embeddings to the x and y axis of the original images. With positional embedding, we can encode the normalized position referring the coordinates of pixels. And this allows the network to capture spatial relationships and patterns within the image during training. And the network consists of 3 models. First, the original initial convolutional layer to elevate the input maps to a higher dimensional channel space. Then we have 4 layers of FNOs, and last, the final 2 convolutional layers to project the feature map back to the target dimension. And in all these layers, we use Gaussian error linear unit as our active function. So the neural network is an iterative architecture as we showed in this picture. And the core of this architecture is the composition of an integral operator K, and then a linear transformation W and a nonlinear active function. And we're gonna introduce the K in more detail. The kernel function K here is specified by a convolution operator within the Fourier space. So we use Fourier transform and inverse Fourier transform as the operation inside this layer. Then you can see the Fourier integral operator as shown on the screen. With this Fourier operator, we can allow training on lower resolution and subsequent evaluation at a higher resolution, all without exposure to any higher resolution data. So in this context, the resolution invariant capability of the neural operator arises from its ability to generalize across resolutions. By learning abstract and scale-independent features during training on lower resolution data, the neural operator can effectively extrapolate its learned knowledge to higher resolutions during evaluation. To evaluate our model, we selected 3 datasets from medical data. First one is pericardium segmentation in low-dose CT scans. This is a large dataset with 154 low-dose CT scans with annotations. And second, we have left atrium segmentation in MRI. So this is a very small dataset with only 20 samples. And the last, we have hollow cell segmentation in microscope images. In all these 3 datasets, we treat the data as 2D slices, and we train our models with 64 by 64 images and evaluate them on different sizes and resolutions. We also use UNet as the baseline of our experiments, so you will see the results here. So in this slide, we can see the results of the pericardium segmentation. Basically, we have the CT scans on the left side, and then the ground truth of the dataset, and then the predictions of 32 by 32 pixels to 256 by 256 pixels. So we can see in these datasets, our FNO model maintains quite stable performance in mean intersection over union, dice similarity coefficient, and also the sensitivity compared to the UNet models. And there is a experiments results on another dataset of left atrium segmentation. We can see the experiment results of hollow cell segmentation here. So analysis of segmentation results reveals that in all 3 segmentation tasks, and for image sizes greater than or equal to 64 by 64, FNO models consistently generate stable and promising segmentation results compared to UNet models. These visualizations underline the robust performance and effectiveness of FNO models in various image sizes and datasets. In addition to evaluating segmentation accuracy, we also find that FNO models shows a relatively lightweight architecture in contrast to the UNet model. In one of our previous experiments of the left atrium segmentation, we used only 20 MRI images for experiments in which we only used 90% for training and the other 10% for testing. So we think this is a very small data set. So that's why we think it's very interesting to look into the impact of varying training data amounts on FNO models. So here we conducted an investigation into this impact, and to ensure the diversity in our experimentation, we focused on the pericardium segmentation dataset. Because this is a relatively larger dataset with 154 CT scans. So the figure here shows the dissimilarity coefficient of the FNO models trained with different amounts of data from 25 to 9,000 images and evaluated at varying image sizes from 32 by 32 to 256 by 256. Interestingly, the FNO model, even when trained with only 500 images of 64 by 64 pixels, shows the ability to produce acceptable segmentation results. Also, our observations from the figure indicate that FNO models showed relatively stable outcomes when tested on images of equal or larger sizes compared to the training set. So these experiments showed the robustness and effectiveness of FNO models, particularly in scenarios with varying training data quantities and testing image sizes. So in conclusion, we used the resolution invariant capability of NOs. So we introduced a novel medical image segmentation model with FNOs that allows us to train segmentation models on low resolution images and generating of high resolution segmentation outputs. And we evaluated this dataset across 3 diverse medical image segmentation tasks, and these all show constantly precise and stable segmentation on images of the same or larger size than the training data. In the end, we also investigate the influence of the training data size, and findings indicate the model's capability to manage limited training data effectively. However, there's also a limitation of this model. There's 2 main questions here. One is the computation cost of this model, because we use Fourier transform and inverse Fourier transform in the Fourier neural operator. So this will significantly increase the computation cost of each layer. So if we want to apply this for larger images or larger data sets, this might be a problem of very high computation cost. And also, there's still a question whether we can generalize this model to other segmentation tasks. For example, not only medical images, but general images. So thank you for listening. And if you have any questions or suggestions to our work, please don't hesitate to send us an email.